Okay, all right, so let's just recap a bit what we were doing last lecture. So the basic idea was to do measurements in bases other than 0 and 1. So this is what we were used to, but the new concept here is you could measure in some other bases like S0, S1. And so this is an example, measuring the plus minus basis. Key point here is that in a different basis, these coefficients are different. So that means the probability is also going to be different. But otherwise, basically, these formulas for the probability and so forth are the same. And showed you basically how to work with these measurement operators. So if you've got measurement in plus basis, then you would construct a measurement operator like that, and you can calculate probabilities in the same formula. So there's basically two ways of doing it. You can change the basis, look at the coefficients, or you can do this measurement operator and get the same answer. And we're looking at this kind of the implications of what quantum measurements in other bases, what this actually means. And one way that this is different to classical cases is that, so classically we're used to the fact that we have something in a different state, we can read that out, right? We can do a measurement, figure out what the state is. This is what, basically your computer does in your memory. You've got some information in the memory of your computer, and if it needs to access some information, it will just read it, right? Reading it is basically perfectly doable kind of process. So in this language that we've built up, basically this means you're measuring states like 0 and 1, and the measurement is in this basis, and you can do this with 100% success. You can actually also do this also in the plus minus basis. Is actually no different, even though this looks like more of a quantum example. But if you have sort of non-orthogonal states, so the new thing here is that basically like these states, like 1 and minus and plus, these are not orthogonal anymore. So if they're not orthogonal, then basically you can't distinguish them anymore. So it doesn't matter what measurement setting you use, you will not be able to completely figure out what this state sequence is. So if somebody sends you a bunch of information like this, encoded in 0, 1, plus, minus, you won't be able to decode it perfectly. Like there's no measurement you can do to figure out what the state is. There will be some error in there. It's just talking about how this is not a good measurement to do to distinguish the states. And then finally we talked about quantum tomography, and this is basically where we do lots of measurements to try and figure out what an unknown state is. So Alice is sending this state. She knows exactly what that state is. Like she made it. She knows that it's that state. Bob, this guy does not know what it is, right? And he wants to do a measurement to figure out what it is. Now, the only thing he can really do in the quantum case, because he doesn't know like anything about the state, doesn't know the basis or anything that he should be measuring in, the best he can really do is to basically get her to send the same state lots and lots of times, do some measurement, and based on the statistics of that measurement, try to work out what these parameters like theta and phi are. So I cooked up some simple protocol to achieve this. So basically, for example, firstly, if you got a state like this, you measure in the 0, 1 basis, and then get the probability. So that would actually already involve lots and lots of measurements. Maybe like 1,000 measurements to properly get these probabilities here, right? So, and then taking arc cos rather, then you get the theta. So Tonjo, you had a question last lecture, and so I looked at it a little bit again. I think you're right. So yeah, I think that this parameter has to be limited to the range 0 to pi. And if you take the negative solution to this arc cos, then I think that does mess things up. Just something I didn't fully realize. But I mean, this protocol is just sort of maybe just a simple illustration, not something that I've actually just made up. So I didn't really think about the subtleties of it. But yes, so we'll do a bit later. We'll come back to this point again a bit later. But yeah, these parameters here are kind of the same parameter ranges as like spherical coordinates. And so phi goes, well, you can do 0 to 2 pi, but actually theta only goes 0 to pi. And when you take the arc cos, it kind of needs to be in that range, at least for this protocol. Otherwise, you get an extra minus sign, and then I think you predict the wrong state. Okay, so I should kind of write 0 to pi here. And then to get the phi angle, then we measure in the plus minus basis, and then you can just do a little bit of algebra to figure out what the probabilities of the plus and the minus are, and it turns out to be something like this. And then to get like this phi angle, then we can just subtract these two probabilities just to get rid of this a half, just makes it a bit easier. Nice little formula here, and then we've already worked out what theta is in the correct range from the first step, and then we just take the arc cos of that, and that's it. So, so you can work out the angles in this way. So, yeah, I mean, in reality, actually, you need to do something a little bit more than this because, of course, you can never prepare the state like perfectly. There's always some noise in there, and when you account for that, which we're going to do this a bit later with mixed states, density matrices, then there's a kind of another degree of freedom that you need to take into account. So you actually need to do kind of another measurement for the qubits. But let's not talk about that now. And yeah, tomography, it's called tomography because it's like looking at the quantum state from different angles, different bases, different coordinates, and then you kind of figure out what it really is. So just to finish off this slide set, why don't we just quickly do this practice question. So suppose we have something like this. So Alice has like 2,000 copies of this state. And she sends them all to Bob, and then Bob is going to do some kind of measurement to try and figure out what this state is. Okay. Now, so Bob first measures in the 0-1 basis, so he's following my protocol. Measures 0-1 basis, uses the first 1,000 qubits for that, and you get 352 in 0, and then the others in 1. Right? And then he goes and does the basis measurement in plus minus basis, and gets 853 in plus, and then the other remaining in minus. So from that information, try and work out what the state is. Might need some formulas that I had were like so maybe these are the key formulas that we need. So in the Z basis, or maybe just a 0-1 basis, and P0 minus P1 was like cosine of phi, and then when you do in the plus minus basis, then P plus minus P minus the cosine phi sine phi. So all the information you need. angles. Okay, so the first one is saying is theta of 120 degrees. Oh, what's the confusion? You maybe turn it to radians per theta. Yeah. Okay, 2.3. Well, answers which I got are just 5.3. So simple calculator work. Do it. Let's see. Oh, 3 is about 2. Well, seems like it should be a bit closer to that. So I mean, for the first one, 0, 1 basis, basically, for this one, P0 should be 0.352, right? And then for this one, it should be 0.6, yeah, like that, right? So, 0.352 minus 0. Wasn't this in scientific mode? 648, and arc cos. Okay, I can't use my calculator. 0.352 minus.
First one is something 1.871.
Right. So maybe what it was times by pi. You get 1.87 or not?
Yeah.
Okay, you do get it. Okay,
Yeah,
okay. Yeah, right, yeah. 1.87 radians. And for the second one, so P plus is 0.853, and then P minus is 0.147. And then divide by sine of the angle. You get where I get?
Yeah.
74? Okay, that's good. That's a relief. I didn't mess up this calculation. Okay, everybody okay with that? Everybody? Yeah. All right. Then let's move on. That's the last slide. Okay, so this is actually kind of a related thing of observables. So up until this point, we were just sort of saying how you do a measurement, and then finally you get probabilities. Now, quantum systems are like real physical objects, right? They're real particles. And when you do a measurement, actually, usually probing some physical property of the system. Like trying to find the energy or maybe the position or something like this. So how do we go from measuring probabilities, which is basically what we've been talking about up until now, to actually getting like physical quantities, like it's like here's a particle. I don't know what the position is, right? Not just some probability. How do we go between probabilities and actual observables? So what we'll see is that eventually we do still do a quantum measurement, because after all, the measurement is trying to measure something about the system, right? So we can't really get around not doing a quantum measurement. But I mean, it's like the next step. So what this guy is doing is trying to figure out from those probabilities what a particular observable is going to be doing, or what it is. Okay, so okay. Okay, so I think I kind of said what's on this slide already a bit, but just to repeat it a bit in the context of this slide. So a quantum wave function contains like the full information of the state, right? So if we go back to this example where there's some electron and it's going through some channel, at any given point in time, we can say that the state of the electron is some kind of wave function. And that is supposed to give the full information of the system, right? So if it's giving the full information of the system, we should be able to work out from that, so what's, some of its important quantities, like the position or velocity or maybe angular momentum or energy. How do we figure out what those things are given the wave function, right? And as I said, it has to be connected to quantum measurement, because after all, it's sort of like we're asking the question of, so what's the energy of the system? Well, to find out, you're going to have to do a measurement to figure out what the energy is, right? And so it inevitably kind of involves a measurement process. So I think it's good to just sort of start with an example of how you actually work out an observable. And so let's look at this kind of made up example, but maybe not too unrealistic example of, consider there's a particle and it's in one of these boxes somewhere. Okay? So there's maybe 8 boxes here, actually, maybe more even, lined up, and the particle can be in one of those boxes. Okay? Now, classically, basically this is like a guessing game, right? So it's in one of the boxes. Don't know which one. It's in one of the boxes, and so in this case it's in box number 3, and the boxes are lined up in a line like this, right? So and they're evenly spaced. So actually, which box is in is also basically telling you where it is too. Right? So the fact that it's in this box actually tells you that it's in position like 3. Maybe these are like spaced 1 millimeter apart or something like that. So it's some ruler. It's like 3 millimeters this way. Quantum mechanically, the state doesn't just have to be in one of the boxes, because as we've been saying, the particle can be in 2 places at once or 2 states at once. So in this case, it could be in like 2 boxes at once, right? So the state is not just 3, maybe maybe it's sort of partially in 0 and partially in 3, this kind of stuff. And then we know how to write that quantum mechanically. We write that in terms of a wave function like this. And here, basically, these states, 0, 1 to n, this would mean basically that the particle is in this box, and number 1 means the particle is in this box, and so forth. Right? But quantum mechanically, we can have a superposition, and then there could be some complex coefficients in front of these. And then so it could be basically written as a state like that, where it's a superposition of the states in each of these boxes. Now I said this was maybe not too unrealistic, and I mean that because actually you can do a kind of experiment like this, and so people have been able to do experiments that look a little bit like this. What it kind of looks like in real life aren't really boxes, of course, but they have like atoms, and if you shine a laser and kind of focus it, and if you use the right wavelength, and you put this whole thing in a vacuum, so there's no air, molecules bumping into the atoms and so forth, it doesn't get disturbed, then actually you can kind of levitate the atoms in midair like this. Shine a strong enough laser beam actually. So the laser light is actually strong enough to hold it physically in space. Okay? And if you've got an array of lasers like this, then the atom could be here or here or here, or it could be like in two places at once. So it could be sort of kind of partially here and here. Example. You can do this kind of experiment if you're interested. You can look in this paper. So in real life it would look a little bit more like that, but let's stick to the boxes example. Now, say I've given you this situation where the state of the particle is, it's somewhere in one of these boxes. Right? Now, I want to figure out which box it's in, right? I want to figure out where is the particle. So what I would do is something like I get a whole bunch of these measurement boxes, and basically I'd kind of measure which state or which box it's in. So basically I would, in a single run of the experiment, I would like prepare that state, and then I'd turn all these measurement machines on and set it, and then make the devices tell me. So so which box is it in? Right? And what's going to happen is that it will randomly like detect. Like for example, maybe on one time, say this detector will detect. It would say, okay, I found it. So the box is it's at number 5, right? And then all these other ones will not fire, right? They would not detect anything. Maybe on another time, it would be number 5, it might be number 3, and then each time you do it, it's kind of random. And it's random because quantum mechanics is basically random when you do a measurement, because we've been discussing stuff like this. So what you're going to eventually get is a kind of a histogram like this. So say you repeat the experiment 1,000 times. Right? And then you start to get a histogram. You build up a histogram of, okay, which box is it in, right? So maybe here, the most likely one is in number 5, but sometimes it's in some of these other ones. Right? And so, the number of counts that you would get would look like this. So for example, this one, it would be like the modulus squared of the coefficient of this wave function here, multiplied by the number of times that you did the experiment. So if this is 1,000 times, then it'd be 1,000 times whatever that probability is. Of course, that's a number between 0 and 1, so it'd be some number between 0 and 1,000. So you get that, right? Okay, so now, after all, what we're trying to do here is to figure out, so where is the particle, right? So if we're saying, originally that was the question. We were trying to say, okay, I want to know the position of the particle. So, of course, it's randomly coming out in different boxes. So it's, I guess the answer is that it's not really in any of them. But actually, we know very well of a way to handle this type of situation, right? So, not just quantum mechanics, but if you just have some kind of random variable, then we know how to do things like we can calculate averages and variances, and we know that it's random, but we can still talk about averages and quantities like that. So this is exactly how we handle this in quantum mechanics too. So because these measurements turn out to be random, okay, so it's random, so it's not really in any one of the boxes, fine. But I mean, you can still talk about an average of the position, right? So after all, this thing is basically measuring the position in the end, right? So this is the position from 0 to 7. Okay, but so for example, we could just take the average of this because these are basically probabilities, and then say, okay, it's random, but the average position is like 4.3, for example. So basically what we do here is we look at probabilities, right? Probability, and then we multiply it by the position, and then we sum over all the different outcomes. You know how to calculate an average, but that's basically what we do here. And the notation that we're going to use for average is this kind of brackets thing. That brackets something basically means the average of x. And we don't have to stop at just the average. We can do other things like calculate variance, and we can basically, because the quantum wave function, after you measure it, gives a probability. I mean, anything you can do with the probability distribution, you can do with the quantum wave function in the end, because the quantum wave function really gives a probability, right? It gives some probability distribution. So you can, whatever quantity that you wanted to calculate from probability theory, you can just apply it to quantum theory. So, next simplest thing is to calculate the variance. So, variance is, in this case, for example, here's the position. So you calculate position squared average minus by square of position. So you calculate this thing, of course, this is how you calculate it. Here's the probability, x squared minus by this is the average. And, standard deviation is just square root of that. Obviously measures the breadth or width of this distribution. In this case, it will be something, standard deviation will be something similar to this range. Okay, so that's basically the way that we turn probabilities into an observable. Essentially, we just take a kind of a probabilistic approach, and we would calculate averages, things like that. So this was just one example where I just took position as the variable in question. But actually, you can do this really for any quantity. So if you were to say, okay, what's the average energy of something, then of course you'd need some kind of different measurement, of course, because this time now you're not measuring the physical position. In the case of position, it makes sense you have to measure the position of something. You put the detector there, and it only fires because the particle is there. pretty straightforward to kind of measure position, right? To measure energy, you need to do something a little bit different, and I'm not really going to go into that, but conceptually it's going to be the same. So, somehow you have some measurement device, and basically it's going to measure the energy of the particle. Now, in quantum mechanics, the energy might not be like a fixed energy, right? So you might have a quantum state that is like so maybe you have different energy states, right? So this might be, say, energy levels of an atom. So maybe like this is the lowest energy state, this is the second lowest, and so forth. And the state doesn't have to be in just like one of these energy levels of the atom, right? It might be in some combination of the energy levels of the atom, right? And then what you would do to work out what the energy is, essentially say, you find that the probability of the state being this lowest energy is p0, and the probability is 1, the probability of this one is 2, then you would say, okay, fine, average energy is again just find the probabilities, and then here's the energies, and then just average, right? And the probabilities, actually, we know how to work it out if we know the wave function, because it's just wave function modulus squared, and that would give you the average energy. And this goes for basically any quantity. So so if this was energy, I did position. Maybe if it was momentum or something else, it would be basically always the same story. Okay, so that's the basic idea, but now let's kind of make some nice mathematics out of it, basically. So what we're going to do is let's sort of generalize this whole idea here. Okay? So suppose you got like some observable Q, okay? So this might be position, energy, something that you want to measure about the system. Then basically what this observable always has is there's some states where it has some definite value, okay? And so this one, let's call this n, and this will form a kind of a basis. And each of those definite values, definite states for this particular observable will have some definite values associated with those states. Okay, so let me just explain what I mean by that. So for example, in this example, we were trying to measure the position, right? Now, the states where we have a kind of a definite value associated with them are like these states like in the boxes. So, maybe here's better. So here, if the particle's in this box, it's in state 0. And that state has a definite value of 0 because that's the position where it is. This one is state 1, this one, and that has a value of 1 because that's where it's located. Another example of this is here. So I have some physical system, and basically here are some particular states where it's in a definite energy level, right? So here's the ground state, here's the next excited state, so forth. Those states, that's the state, and then each one of these states has a particular numerical value associated with it. So, I don't know what this is, but maybe it's an atom. Maybe this energy is like, I don't know, -1 electron volt. This one would be something a bit higher, -0.5 electron volts. Something like this, right? So these are, these are definite, actual, numerical values associated with that state. So there's always there's always the state, and there's always the number associated with that state, right? So, so basically when we talk about an observable, we're basically talking about like a pair of things. So we're talking about, okay, so here are all the possible states that we have, and then here are all the values assigned to those states, right? So there's the states themselves, and then there's the actual value. So my example here, so n are the, say, position states, and then this is the values of position, this is the energy states, and this is the actual numerical values of the energy. Okay, and then, so suppose we've got some state, and it's in a quantum state, so it's like a superposition state, right? So we've got these states and some coefficients associated with it. And as I just said over here, the probability of it being in this nth state is just the modulus squared, right? So the probability is just modulus squared. Okay, so I've written an here, so an modulus squared. Another way to actually write this is like this. So if you take the inner product of this with n, okay, let me just write it out. So that's the same thing, because you work out what this is. So psi, I've written it as sum over these things, but we've already used the variable n, so we better use a different variable. So let's call it n dash. So n dash, okay. And these states are orthogonal, right? They're orthogonal and normalized. So, so this will be like a0, a1, an, n. And, n is just a fixed number at this point. So, somewhere in this sum here, there will be the nth one. And all these other ones, like a0, a1, so forth, all these ones except for the nth one, so n. So say this is the one, right? And then so all these other ones will be 0, except for this one, and then this is 1. So basically this is 1, right? So, like the way delta functions work in integrals. So
each states are still orthogonal to each other.
yes, so all these ends are orthogonal to each other. Yeah, this is why you can do this. Oh, sorry. Yeah. Sorry about that. So this is A. Okay, and then it's actually an modulus squared, so that's why it's this thing, modulus squared. Okay, so now when I say I want to find the average value of some observable, like Q. So what I mean by that is that, well, I like in this example here. So I'm going to average over the the value, meaning that I take the probabilities that it occurs and multiply it by the value, whatever the thing that is I'm averaging, like is it energy, position, or thing. So basically what that means is that when I'm saying I'm going to take an average, or when I'm going to take the average of the observable Q, what I kind of mean by that is that I'm going to look at the probabilities, and I'm going to look at the values that they come out, that each of these states are assigned, and that's my average, right? Probability times the value. And like I've already said here, you can rewrite the probability as modulus squared of the wave function. So the average value will be modulus squared of the wave function times the value. Okay. Yep. Okay, and so now that we've sort of got a more general formula for the thing that we're trying to calculate, so average, we can actually do a kind of construct. We can take this sort of mathematical formulation a little bit further. And what we can actually do is to define this observable operator. And this is actually a matrix. And the way that it's defined is like this. So here's the values. This is Qn of the values that we were talking about. And then we just take the outer product of this, the thing that it's associated with, the state, with itself. Okay. And we can actually just create a quantity like this. And we're actually going to call that the that's the observable operator. And why do we want to do that? What it does is to actually kind of make a it kind of makes the this kind of procedure of calculating averages a little bit more actually automatic. So so up until this point, what we had to do to sort of calculate averages is sort of do something like, okay, we've got the wave function, we've got figure out the probabilities. Okay, we've got these values, and then we do an average over all this stuff, right? Now that's okay, but by introducing this operator, actually we can sort of simplify that whole thing. So it's just we can just throw it into the mathematical machinery, and we almost don't really have to think about how to calculate averages. And the way that it works is that if you want to calculate the average of something, then, so say you wanted to calculate the average value of this observable Q, once you've constructed this operator, all you have to do is just calculate this quantity. Basically, take this quantum state, and then you have the observable operator. So this is actually a matrix. Then you just sandwich the states. So the state is like the bread, and then the operator is like the thing inside your sandwich, right? And if you calculate this this quantity, basically that will turn into the average value of Q. So this kind of makes it a sort of a very kind of powerful kind of process, because you don't really have to even think about anything. You don't have to be messing around with figuring out probabilities and combining that and taking an average. Just calculate that quantity, and then it just calculates the average, right? Okay, so why is this the same as what we've been doing? Well, let me show you. So, okay, so we've got this quantity Q. Okay. I'm going to omit the limits on the summation. So the way to think about this is that this is actually, you can literally write it as some matrix like this, right? So it's going to have, it's going to be a matrix that looks something like this. All this stuff is 0. Okay. The state is this. And as we've said, the state is actually a vector, right? So the state actually is going to be something like this. Okay. And then, I guess just a good measure, well, maybe I should have written it sort of over here, but the bra of this state is and star and then this is actually like a row vector, right? Okay. And so what we're proposing here is that if you want to calculate the, here's our wave function, conjugate wave function. If you want to calculate the average value of some quantity, we first construct this matrix or the operator, and the average value of Q is supposedly this one, right? So what this one should be, so from our discussion, what we're doing before, what this one should be is actually this thing here, this quantity here. So it should be, so let's sort of write that. So it should be supposed to be that, okay? Now let's just verify that it really is that. So, well, maybe in this case it's actually pretty easy just to do the matrix version. Maybe we can do both. But essentially what we're going to be doing is just doing, this bra times by this matrix times by this K. Okay? So this is essentially what we're doing. Okay. And so we can just do this first multiplication here. This is the same. So because this is diagonal, you can kind of see that this one is going to be A0, Q0, A1, Q1, AN, Qn. And then this vector now is going to multiply by this row vector. And basically this will now become a number. So it's A0, A0 star, Q0, A1, A1 star, Q1, dot, dot, dot. And of course, so this is just A0, absolute value, Q0, A1, absolute value, Q1. And so in summation form, that, which is exactly the thing that we said is the average. It sort of looks a little bit like a bit overkill to introduce this matrix here to just to calculate this thing, because a lot of this matrix is just zero. Looks a little bit overkill, but actually what it will turn out is that this formalism, actually you can generalize it so that actually the this matrix might not be just such a simple matrix, and especially in that case, like this kind of way of writing it actually helps a lot to just make the process of calculating averages like automatic. Just so that you can see how to do it so that was sort of in matrix notation method. Now in the other method here, let me just go through it as well. So let's just repeat the whole calculation in just with sums. So what we're going to do is calculate this thing. And so let's first calculate q times psi, and then so remember that, so this is actually what we're doing is it's often good to sort of mentally keep track of so what's a matrix, what's a vector, so I think I've explained it already, but Q is a matrix, and then the size of vectors. So basically, matrix times vector should be a vector, right? So so let's evaluate this then. So when you substitute these definitions, so that's Q, and then we're going to write psi, but we have to make sure that our labels are not going to get mixed up. So always put a new label here. And so summations, you can always interchange the order and just get them out front. So we'll have two sums like this. Got a Qn, got an An. These scalars, again, you can put the ordering any way that you like. And we've got an n, and then this one and this one, we've got an inner product between them. We can use our delta function, so we can write this as a delta function. And when you have a delta function, basically the only terms that survive in this double sum are when n is equal to n prime. So basically, we can just, n has to be equal to n prime. So change all our n primes to n's. So this one will be Qn, An, n. Okay, so that's Q times psi, and this is supposed to be a vector, right? And so we can just see that this is a vector because, well, it consists of these unit vectors and then some coefficients here. So that's definitely a vector. Okay, and then now let's go on to evaluate the full thing. So Q should be psi, and we've already worked out what this thing here is. It's just what we did there. So then let's do that. So n, An star, maybe this one will put primes on this one. I've already written that like that. So that's that part. And this one just copy Qn, An, this. Then we do the same kind of thing. So we've got two sums, n and prime. And then all these coefficients. We've got Qn, An prime, star. And we've got n prime, n in a product. So this is a delta function. So one of these sums collapses turn the n prime into n, and so we've got qn, an star, and that's equal to qn of absolute value of n squared. Obviously that's a number, there's no more kets or bras or anything like that. So, and so finally, this explains why we're using this funny bra and ket notation, right? It's because that kind of looks like that. Like that's, because this notation means average, right? Kind of looks like that, it's already suggesting that you should do that, right? That's basically why we're using this notation. No? Yes. I like it. I mean, it's like, I think the best kind of notations. So when I'm writing papers and stuff like that, often I'm like going, what's the best notation to kind of explain this thing? And the best notation is when, like, you can just sort of do things and then you just look at the formula and it's already telling you what you should be doing, right? So that's why I think it's an ingenious notation, because you can say, okay, how do I calculate averages? Oh, well, do the thing that almost looks like it. Yeah, but anyway, so that's that shows that this is one way to write such observables. And so in quantum mechanics, basically over here it was sort of like a little bit abstract. We were saying, okay, so here's an observable Q. Q was sort of an abstract thing. It's sort of just like trying to calculate some quantity, right? But now actually, this is not just a sort of an abstract thing where I'm saying I want to calculate some quantity. It's an actual mathematical sort of quantity, which is actually this matrix. So essentially, because this contains the whole sort of information of the thing that I'm trying to work out, right? That's the quantity which I'm interested in. So this operator is actually more or less the definition or the encapsulation of what this observable actually is, right? And the state, on the other hand, is really the state of the system, and that contains the information of what kind of state it is. And this operator really has the information of, so here is basically all the possible outcomes that you can have, and here are all possible values that are associated with it. Okay. All right. So as I said, it almost looks a little bit overkill to introduce these operators here, but actually you can. Where it really helps is when you look in other bases, and what was very simple about this example that I had here was that my state, the state here, the basis that my state was written in, n, just so happened to be the same basis as the observables, right? That's not always the case, right? Because it's just to give a tangible example, maybe suppose this one was like positions, right? And I'm saying, okay, here's my position number 1, position number 2, and here are the states associated with it. But I mean, I didn't have to write my wave function in terms of the position basis. Perhaps like I had my wave function, but it was written in something else, like the energy basis. Perhaps these ones were actually energy. Say energy 1, energy 2, and so forth, and you have coefficients. And then this one was position. So you don't necessarily actually, because these are independent things, like this state and the observable. I mean, they don't necessarily have to be, well, they're sort of self-standing things, right? They can come together and you can calculate things with them, but I mean, not necessarily, right? So what I'm going to do here, maybe it doesn't make sense to fully start it, but I'll just give you an idea of what we'll do next lecture. So what if, you have another observable, it's called R, but that's actually written in some other basis, right? So it's not the same basis as the basis that we had for the state. Then essentially what we have to do is, well, we could do a few things actually, but one way to go about it is to then, we can have our state, and then we're going to have to rewrite our state in this other basis, right? Then at least if we've got the common basis, then we can do something like what we already did. So what we have to do is we start with our original state. We do a basis transformation, just like we did a couple of lectures ago. And then once we've written it in the common basis, which we know we can do, then the story is the same. We just do our probabilities according to the coefficients in the new basis, and then we take the average of this R, right? And then the R would be modulo squared, but then it would have to be these B coefficients, the coefficients in the new basis. So that's one way to go about it. Maybe we'll kind of leave it there, but basically using this formalism that we have, actually there's another way to do it, which basically again we just do the same formula, and then eventually it all comes out to be the same thing. And so just by using this formula, you don't have to worry about any different bases or anything like that. This R could be written in this different basis, the psi could be some other basis. Stick it into the formula, and then it'll all work out. Okay, so I'm losing my voice, so I think that's a good place to stop for today.
If I wanted to describe observable in like a simple way, could it be like it's just like the position of a and like the position of a thing in the state, like in a state system? Is that what that means?
So
Like for Q.
for Q, well, Q, I've just sort of generalized it to be any observable that you might be interested in. So the Q could be position. In that case, the observable would be position, and in that case, the states would be like states which are in definite positions. So state number 1 would be in definite position, like 1 meter from here. And then these Q's, the little Q's, these are the values that you associate with it. So, for example, like these things have units of, if it's position, it would have units of, say, meters, right? So Q has, actual units and dimensions. This is just, again, it's a quantum state, but it's the state where it's in a definite position. But it doesn't have to be position, because that's why I call it Q, sort of a general observable. So if we're talking about energies, then it might be the definite energy states, and this would have different, definite values. It would be measuring joules and things like that. But normally we deal with things like position momentum, but you can have position energies, but have also momentum. Actually, any value really. Okay.